100 years will be required the same in the next 10 years. And in 10 years, we need to double our capacity of generation. And in the past 2 days, I don't know if you have seen, there are many presentations. So just with the hydrogen application, Oman will be requiring around 34 gigawatt of power just for the hydrogen, which is 3 times plus more than what's your current production. The other mega trend is the unpredictable consumption and unpredictable production or generation. So we have renewable coming in. Renewable is something unpredictable. You depend on the sun, on the clouds, on the wind, so it's something that you cannot predict. Similarly, the power consumption is unpredictable. When you talk about electrical vehicle, is a load that is not static. Today you are charging here, tomorrow you move to another place, and imagine the seasonal movement of people, so you will have a load that is moving in the geography, and that creates unpredictability in the consumption pattern. We talk about also the new stakeholders. Today there are many companies involved in the power delivery to the customers. You have generations, you have retailers, wholesalers, you have even utility companies that don't own any electrical asset. These are aggregators. These are companies who they are just an intermediary between the producer or the wholesaler and the retailer. So new stakeholders, new business models, very sophisticated business models that deliver power to the people in a very new way. And of course, human resources. The today generation, the people, the youth, the young people now managing the grid have modern ways of looking at managing the grid than the previous generation. So they have a certain user experience where they expect that everything should be easy, accessible, more visual, right? They depend a lot on digital devices. So this young, you can say human resources now managing the grid, they require the same user experience they do it in their daily life when they are managing the grid. And digitalization everywhere, of course, you know, the grid, whether it's transmission, distribution, even the low voltage today is full of digital devices, of IoT. We get a lot of data from the grid today compared to the past. We talk about the IT-OT convergence. Traditionally, the OT system used to be disconnected from IT. Means your SCADA system, your smart metering used to be in a network, and then all your IT, your top floor systems are completely separate. But today, the business requires that these two areas need to be more and more converging, and maybe the IT team or the customer service department will require information from the SCADA, from the consumption, and vice versa. Legal requirements also today, the grid is highly regulated, so you have regulators, legal requirement, cybersecurity requirements, so there's more and more pressure on regulating how the grid of tomorrow is managed. And of course, another trend, which is the bidirectional power flow. There's no more flow from top to down. There's no flow can come from a household, from a renewable production. A rooftop can be injecting power back to the grid, and that creates complexity. The other element here among the trends is the accelerating form. So all these trends are going in an exponential or parabolic way. They are not progressing slowly. They are not, let's say, a normal pace. They are going at very high pace. And that can create one day, you know, a crisis. How do we deal with this? Let's say, imagine tomorrow that you have a lot of adoption of rooftops without proper planning. What could be the impact on the grid? Now, how? So what do we expect from the smart grid? How the smart grid should look like? We expect the smart grid to be reliable. Our dependency on electricity is becoming more and more than any time before. We cannot afford a power cut for even few minutes. Maybe 10 years ago, we could afford a half-an-hour cut. We were using power just for a few things, but today, we are over-dependent on electricity. We cannot afford outages. So reliability, very important. Resilience, even if there is a problem, the grid should be able quickly to restore. Even if there is, I don't know, a hurricane or whatever, a crisis, the grid should not collapse. It should be quickly coming back to normal. The grid should be efficient, means less losses. You should not have waste in your grid. It should be productive. How can I do more with less? How can I put more customers on my grid than before without adding new production capacity? So productivity. Digital. The smart grid should be transparent. He should tell me what's happening. He should tell me his heartbeat. Where is the load? Where are the problems? So he should be more talkative. And secure, of course. We put digital. Digital is good. It gives you visibility, but cybersecurity is very important. Sustainability. The whole sessions in the past 2 days were around sustainability, adding more clean energy into the grid. And of course, a smart grid is a grid that does the right mix of energy sources in such a way it reduces the CO2 footprint. So you will have, anyway, you will not have I think having 100% renewable will be a dream, but you will have a mix. Now the smart grid should be smart enough to say, I will consume the maximum capacity from renewable, and then the rest I get it from conventional. Scalable. The grid should be scalable, means we can grow. It should be, now the economy is growing, so the country is growing, your economy is getting better, so you will need to scale up your grid. So it should not be limited or reaching the boundaries very, very easily. Now the what. Okay, so what do we put in a smart grid? This is a typical IT/OT architecture, so we go a little bit deeply technical here. So an ideal digital framework in utility should look something like this. Means on the bottom you have the OT side, so your field devices, your protection relays, RTUs, all the devices in the field, smart meters, right? Those are there. Then you have your SCADA system. Most of you are aware, if you are in distribution, you know what is SCADA, so it's the real-time operation and control of the network. Then there is a new development today, we call it network applications. So this is the analytic layer that sits on top of SCADA, because SCADA is purely reading data and display on the screen. That was good enough in the past when the number of data was very few. So an operator can take decision based on few information on the screen. But today grid is sending a lot of data to your SCADA. You cannot, with your eyes and your brain, assess or analyze hundreds of data changing on the screen. That's why we require analytics, so we let the machine digest the data and tell you what to do. So we call them decision support applications. So the operator is sitting, the application is running, and it tells you, look, there is something happening in this area. I suggest you to do this to avoid the failure or to balance, let's say, the network. And there are plenty of applications in that area. So I will not go through all, but a typical digitalization of a utility, this is how it looks like ultimately in the end. Of course, not all utilities have all this today, but it's something that you can plan. So, okay, this is my end game. One day, any DC, for example, will look like this, but let's see, how can I reach there? You need to do planning, تخطيط. So, you need to plan your digitalization journey. So from where we should start? I'm sure any DC today or any utility have something today. So let's see where are you today and where you want to be, and we assess the gap. And then we want to prioritize what investments I should do to get optimal results. Some of the bricks you have seen might not bring immediate result to you, but some of them will bring immediate benefits. So we can plan what comes first. What technologies do we need? Of course, the technological decision is very strategic. Sometimes you should not do a mistake in the selection of the technology in the beginning, especially in systems, large systems like SCADA, like smart metering. It's very crucial in the beginning to choose the right technology. How mature we are, yes. You need to assess your current situation. Where are you starting from? So look, from that honeycomb, I have 2 or 3 bricks already there. So that's your beginning. And then we plan for the next steps. So for that, Siemens is bringing a consultancy portfolio called Digital Maturity Assessment. So it's a 1-week assessment exercise. We sit with the customer, let's say Mr. Digitalization of NEDC, example, and we assess the current situation. Where are you in digitalization today? What are your capabilities, your teams, how they look like? So I have a department of automation, I have a department of telecom, I have GIS. So we assess your current capabilities. And then we do the analysis. We see all the 360 degrees capabilities and we compare them to the industry standard. So look, in SCADA, you are doing good. I think you are 3 out of 5, so that's an area that is good. But let's say on demand response, you are weak. So you see 360 degrees, where are your weaknesses, your strengths, and then based on your priorities, so we also, in the discussion, we'll be collecting the priorities of the utility. So okay, this year or the next 3 years, our main priority is to have more renewable, or we want to increase customer satisfaction, or improve our revenue collection. So every utility has priorities, right? So we define the roadmap, so then we come up with a roadmap. We say, look, specifically for NEDC, this is your roadmap. In the next 2 years, you need to have 1, 2, 3. In the next, let's say, 3, 4 years, you need to have this. So a roadmap of digitalization to aim for the honeycomb that you have seen earlier. So this is a consultancy service we provide it to utilities for the digitalization assessment. So we do like this, I explained it already. We do first assessment of the objectives, your capabilities, current capabilities, and then we propose the initiatives. So what are the projects you need to start with in terms of IT and OT, in terms of processes, so a full action plan in a week. So can you imagine? So it's really very effective exercise. 1 week, you will know. At the end of the week, you'll have a report, you know, where are you today, what is your gaps, and what is your plan to become digital. I think it's the most really effective way of doing it. Then we introduce GridScaleX. GridScaleX is a bundle of software. You know, Siemens has a lot of software for the grid. We have planning software, operations, SCADA systems, a lot of software. What we are doing here, GridScaleX, is bundling all these softwares under one name. It's like, I don't know, Microsoft Office. Under Microsoft Office, you have Word, Excel, PowerPoint that you use in your everyday work productivity. Imagine the same thing, but for your grid management. So when you enter in the morning into your office, you have all your tools there, your planning, your simulation tools, your operation, your renewable monitoring, all the tools there, you click and you see. So in a more integrated way. Traditionally, every department buys the tool that he needs. But today, we are bundling them together, of course, benefiting from the integration, which is very important. We should not see these products as islands. They should talk to each other. Same thing, your user experience today, when you deal with the administration, with the e-government, you expect that many things are integrated, right? Your passport, your mobile, your address, everything is coming in the same place. So same thing here, we want that the different software in the grid are integrated. Say, smart metering is sharing information with SCADA. GIS is sharing information with the smart metering system, and so on. So sharing information will reduce a lot manual work, will reduce mistakes, and this is the beauty of Gridscale X, is really we talk about acceleration. Is really how can we accelerate your digital transformation. And you remember my first slide, the problem, the trends that are happening today in the grid are not slow. They are coming very fast. We are talking about 34 gigawatt in few years. So tripling your network in few years. So that's, I mean, just saying it looks impossible. And of course, our aim is to reach one day an autonomous grid. Imagine that you put your network into autopilot, like the airplane. You put autopilot. Some of the basic functions will be fully automated, and then the operator or the human will just act on the more sophisticated actions. And that's our aim. With Gridscale X, we aim for autonomous grid. Another example is the smart metering system. I think most of you are aware of that. So it's the system where you read remotely the consumption of water, electricity, gas, whatever. Traditionally, we use the smart metering for meter-to-cash functionality, which is automating reading, issuing the bill, and getting the payment. This is why utilities invest on smart meters. But that's a big investment. If you just stop in the first 3 features, that's a losing investment. The smart meter, imagine, you have in Oman, you will reach around 1 million meters very soon. 1 million meters. So imagine every house, you have a sensor. You have a meter that is telling you in 30 minutes basis how much is your consumption, your voltage, your power factor, everything. We know everything about your consumption of water, electricity, every 30 minutes. So that's a big, it's a gold mine of data to know your pattern of consumption, and it can help us to do all these functionalities. It will help in planning, it helps into load forecasting, energy efficiency. So if you have a Tarshid and energy efficiency initiatives, this is where you can use it, and the list go down. We go even to the rooftop PV. When you install rooftops, you need to monitor them. You say, are they efficient? Did someone install a rooftop without informing NEDC, and so on. So EV chargers. So really, that smart metering infrastructure can be pushed to the limit, so we can get a lot more value from it beyond only the meter to cash. And one of the examples I'm putting here with a customer in the region, we are receiving every day more than 100 million data points every day. Around 7 giga, 8 giga of data every day. So, and it's the same here. So very, very important, the AMI. It shows the AMI investment, the P&L, the profit and loss with time. So when you invest on smart meters, you put a lot of money first day. You need to buy millions of meters, install them, telecom, software, it's billions, right? So you see, that's why the first investment goes down very quickly. But then, when you enable the features, you start getting back your investment. If you stop at number 2, which is meter to cash, if you stop just by collecting information and automating the bill, you are still negative. Your investment you're not getting back your investment. When do you start getting back your investment? Is when you go to visualization. Those are valuable data. I want to see it. I want to see a dashboard that tells me X, Y, and Z. Then I want to analyze. I want that the system will analyze those millions of data and tell me where are my losses, where are my outages, where is the area of the network that is more vulnerable with outages. There are a lot of power cuts and so on. So that's analytics. And then acting, taking action. If the system tells you, look, power factor or reactive is high in this place, you need to put capacitor bank and corrective action. If you take the action, you will again gain more. So really, you get your smart metering investment back if you go for 3, 4, and 5 actions. And most of the utilities, they stop in 2. So our role is to pull them towards the positive side. DER Insight, this is for the renewables people, really the rooftops, and that's, I think, very trendy today in NEDC, installing rooftops and electrical vehicle chargers and so on. So this is a software that will allow you monitor the production, the consumption in every house, and see the impact of those PVs and EVs on the grid in terms of power violation, voltage violation, and it can even do what we call disaggregation. Means from the meter reading, I can tell you whether behind the meter there is a PV system or an EV charger, just by checking the pattern of the consumption. And that's very important, because if I want to install PV in my house or a charger, I need to take permission from the utility. I need to send a request, I tell you the size I want to put, etc. You review it, and you say, okay, approve, please go ahead. But there are some people who don't do it. They just buy an electric car, he plug into the plug, or he just put some PV on the roof without informing. If 1 or 2, that's fine. But if you have a high adoption, that will be a problem. So this software will be able to detect, tell you that in this area you have X, Y, and Z production. It gives you if there is any congestion on a transformer, because putting a lot of PV under the same transformer, you might reach the maximum capacity, and you might deteriorate the voltage quality. So GridScaleX, DER Insight, a new product, very, straightforward. In terms of deployment, it takes really short time. I think around 12 weeks, it's up and running. It has 2 inputs. One from GIS, Geographical Information System. So we get all the map or the single line diagram and the topology from GIS. And the second source is the AMI, the smart metering. So with these 2 sources, feed this software, and then you have full visibility on your DER installations. Now, LV Insight, similar one, similar software, but here it's like a low voltage SCADA or monitoring system. We know that SCADA today is for high voltage, medium voltage. LV Insight, you go down to the low voltage. You see how's your network at low voltage. So you see all the, if there are any interruptions, outages, you will be able to detect them, analyze them. You can detect also, do what we call outage management. So if, example, you have 100 meters, they all said, I have seen an outage. The system is able to detect where is the point of failure that affected all these, let's say, 100 meters. These are some testimonies from our customers in the world. So this is American Electric Power. We did for them the PSSE, so this is a planning software, and ODMS. Yeah, ODMS. I forgot to talk about the. So I have only 1 minute for my friends. So digital twin, quickly. Digital twin, very trendy word. You might have heard it a lot. Now, how do we apply digital twin to the grid? So digital twin, what is by definition, is a high fidelity digital replica of your grid. كأنه نسخة حقيقية تاع الجريد in a digital format. What's the purpose of digital twin? The purpose is you will be able to simulate any action you want to do on the grid in a digital world. So before doing an action, before installing a PV in the network or a new load or a new EV charger, you test it first on the digital twin, and then you see the results, then you will be able to apply it. The second big feature of digital twin, very important, all utilities are facing this trouble, is that you unify the network model across the enterprise. I give another example. So if you take, let's say in NEDC, you have planning department, you have SCADA department, you have a maintenance department. Every department has a network model, single line diagram in 2 words. And every department is maintaining or updating the SLD in their corner. There is no coordination, or there is few coordination, or manual coordination, if at all it exists. So you end up by having different versions of the same thing across the departments. Digital twin will remove that. Digital twin, you will have one version of the truth, only one version of your model, the grid model, and then all the departments, the different softwares will take the model from one place only. This, for these guys in American power, electric power, this is a big utility. I think they have 5 million consumers. It's really a big utility. They were able to reduce the manual work and the mistakes drastically just by applying digital twin. And it's the trend. Today, it's getting more and more complex. You need to have a unified single source of the information, and it will help you also not duplicate resources. Imagine you have SLD engineer in planning, one in SCADA, one. You have only one team, they are centralized, and then everybody will get the same information up to date and an information that you trust. I've seen customers, they say, I don't trust the single line diagram I see on the screen. I don't think it's updated. When you start having this and trust, you cannot work properly. You are not sure. You are not sure whether if you open this breaker, the right breaker will open. So digital twin, very, very important as a smart grid thing. Gridscale X, this is with Elvia. This is a Norway utility. In fact, we developed this software, LV Insight, with this utility. So they had the requirement to see more on the low voltage, not only high and medium. They say, I want more visibility on low voltage, because today, low voltage is becoming complex. You have rooftops, you have chargers. I want to have visibility down. So, okay, we developed with them this, and this is now available in the region as well. ODMS, again, another utility in Finland. They were able to improve their reliability by X%, reduce 80%. So yes, this is a good example. This utility used to spend 80% of their time and effort to collect data. I call protection department to give me the latest single line diagram. I call this so manual collection of data. Now with digital twin, with ODMS, they flipped it. Now they spend 20% only for data coordination, data collection, and 80% of their time analyzing. So you spend more time putting your own added value, not doing data collection, calling Mr. X, Mr. Y, please send me the file, and you do it everywhere. This is a real case in Finland. Well, this is another one. So many examples. This is for smart metering also. So I think I will stop here. So thank you very much for your attention. I will give the floor to Manoj with his microgrids. Thank you. We will have 10 minutes in the end for the questions.
Very good afternoon and salam alaikum. Okay, so myself Manoj. And today we are going to just discuss about microgrid, not only microgrid and microgrid control. Like what is microgrid and what is benefit to controlling the microgrid, how it can be utilized. And as we know that Oman is a very big country and they have so much resources for the renewable energy. I believe microgrid, it will be really very helpful to reduce the carbon footprint. So here is my agenda for today discussion. So first we will discuss what is microgrid in brief and how we can control it. Then we'll discuss about some of its function, and then we will discuss some use cases which we can perform through microgrid control. And then in the last I will just introduce that which platform we are using for microgrid control. So actually for microgrid there are a lot of definition, and it can be always based on owner or asset owner, or who is going to develop the microgrid, or who is going to use the microgrid, because some guys they will use just only solar and battery, and it will be microgrid definition for them will be different. Some guys, they will use your traditional generator also. So for them, it's a different. And some guys, they are going to connect this microgrid to our traditional normal grid. So it's different definitions. But some normal definition we can have, like microgrid is somewhere same kind of traditional grid, where we can have generation, we can have distribution, we can have load control, and if required, maybe we can give power supply to traditional grid also. And if required, we can, in emergency, we can take also power from there. So somewhere, if as in the beginning I said, it will be very helpful to reduce the carbon footprint. And somewhere I can say, like even traditional, our normal distribution group, like they can also develop their own microgrid and they can use as a backup. They can supply, for home supply. So as we are with we are having our 2050 vision of the Oman to have the net zero carbon emission. So I think this could really help by seeing the geographical view of Oman, because they have so much. So even you see, even normal system also we can realize as a microgrid, because some they can work in isolated area. Our AC control system, that also can be microgrid. So there are some example, and downside also we can see what is the benefit of that. So we can control thermal control in some industrial site. We can demand charge, because in emergency cases we can use the supply from our microgrid renewable resources. CO2 footprint, because now in these days CO2 footprint, reducing this, it's really the main challenge. And as today I think the main agenda about this IEEE Power Talk, how we can shape our environment and reduce the carbon footprint. And we can have our own microgrid, and we can integrate our all kind of assets. Then major example like parking and fleet, hospital, island, and remote system. So I have given some few example, but these are not the only these one. There are a lot of definition for microgrid. So in general, why we need microgrid. So as I think in the beginning also I said, microgrid basically it's required for, if you'll see the consumer point of view, energy prices are so much high sometime. And in traditional grid, we can see some unforeseen fluctuation, like suddenly due to some hurricane or some natural disaster, natural grid got disturbed and we lost the power. So in that case, we can have our own some kind of backup microgrid, which we can use for emergency power supply. And I would really say always we have capacity by implementing microgrid that we can reduce the CO2 footprint, which is really main agenda, we can say. Then I'll just briefly discuss about what is the benefit of microgrid. From the first slide I was saying, so with microgrid control, we can easily integrate many type of devices, because our microgrid control will operate with the latest communication protocols. So any kind of smart devices can be integrated, like anything. Like if suppose you have battery system and it's supporting the communication protocol, it can be integrated. If you have PV system, it can be integrated. You have genset, that can be integrated. Like any kind of smart device, it can be integrated with microgrid control, and you can fully utilize it. As our colleague also said, that it's not always good to have many devices in your network unless you are not monitoring properly and you are not fully utilizing. It's somewhere, I would say, more invest and less profit. So microgrid controller, he is going to help you here how you can really utilize your full capacity of the assets. So I have just written a few benefit, but it's not limited here only. So maybe we can see here, it can integrate very many distributed energy resources. And as our microgrid controller, now it's very smart, so it can integrate with any kind of network, smart devices. And the best thing about this point number 3, like scalable solution. It's not like that you have developed some microgrid control and tomorrow you want to integrate some new devices, new assets. So it's nothing like that. You have to go for redesign. You can just simply expand it. And same like monitoring and controlling of assets, you can simply monitor and control the assets when it's required, and you can perform all kind of control and monitoring operation on that. And the transparency and efficient maintenance, it's about like you can see all what is happening about your assets, how it is performing, how your load is going on, how like your battery is getting charged, what is the health of this, how it is the health of PV, how is the genset, everything you can see, and you can really be prepared for the maintenance. And in the same way, like it's because now these days, suppose you have only battery system or you have only PV systems, it's very difficult for the monitoring because they are decentralized. They are not the one place. But with microgrid control, you can integrate all of them together in one system, and you can really utilize of them. Then I would say like just one logical diagram we have here. So uh, inside we have our microgrid controller, which can integrate, you can see like PV, wind turbine, genset, even it can have like e-car charging, and it can connect to traditional grid. So many things. And we can find these three kind of things it will support. First thing, economic, because if you are investing something and if you are fully utilizing it with proper monitoring and all these things, it will be economical, helpful for you. And resiliency or reliability, like suppose you have one microgrid and suppose you are taking power or something from distributed, or you have PV, you have battery system, you have genset, something like that. Suppose you have loads and something is feeding to your loads and that source gone faulty. In that case, microgrid control automatically it will decide, it will recalculate, and it will feed from the resource based on the algorithm. And it can also decide whether it should be feed from traditional grid or it should be feed from our like renewable resources what they have. And sustainability, which is from the beginning I was saying, sustainability is the very good points here, where it will use maximum renewable generation, and it will try to reduce the carbon footprint. Then just in simple way, I want to show you how microgrid controls should work. So basically in our orchestra, the guy who is guiding to everyone how to play, what is the level, sound, all these things, he will behave as a microgrid control. So, all other things will be controlled by microgrid control. So he will be like the main conductor who will say, okay, you do this time you do like that. He will just control all of the assets. So this is just next picture. You can see the conductor got replaced by microgrid control. So the guy, he will control all the assets which are integrated in our network. This just next picture, what I said, that you see in the first picture we saw microgrid control, he was integrating all these things. But suppose we have very big network where we have one solar plant, one location, other solar panel, some other location. Here you can have dedicated microgrid controller for for load management, for PV plant, separate plant for e-car charging, and these microgrid controller again they can talk to one central microgrid controller. So it's basically they are in network, and everything can be properly configured, analyzed based on algorithm. It's totally configurable. What you want, how you want, what is your priority, everything is up to you. You can manage your energy, you can manage when to export, when to import. If you are allowed, you can import to grid. If you are allowed, you can export to grid. So then let's come for the functions. Functions means what is the like what is the output? Why we are using microgrid control? So basically I just written down few scenario. So it will reduce your capex, it will increase your capex efficiency and opex efficiency and CO2 efficiency, which is if you'll talk this PowerTalk, IEEE PowerTalk, this is the main agenda. So you can utilize your maximum renewable uses. And in Oman, as I said, being a geographical area, we have, I think, so much potential here to use the wind, we can use the solar. And resiliency means like it can automatically recover. It's a fault situation. And the one good thing what I want to discuss, the last one, simulation. Simulation means we have capability in our microgrid controller that before implementing in real system, you can simulate all the situation, all the use cases. So based on that, you can see that which use cases is good for you. Based on that, you can design, you can develop your network, you can develop your, you can order your like device, everything. So before ordering actual, before configuring or before designing actual network, you can simulate everything, then you can design. I think my voice is clear because sometimes mic is here and there, so I hope. So we have this small device. We call our microgrid controller. It has many features, but it's not limited. As I said, it's fully configurable. If you need, we can add some more use cases based on customer requirement. So like we can have the peak saving, sometime higher energy consumption, we can utilize those with our renewable resources. We have like we can have control over generation, and sometimes we can give the data to market for analysis, and based on that we can decide whether we have to import or export, or based on price and all these things. We can have like islanding or black start situation. Then we can have like, we can control the load, we can set the load based on what we have the power. If we have less power, we can set the like non-critical load. So those kind of things we have many features, and it's not limited. It can be generated new also. So I will take few use cases example just from the last slide, because we cannot discuss all. So basically, tile and control. It's very important. I would say it's very important function. Tile line means basically we say, if suppose we have microgrid, the point it is connected to the traditional grid, that point is called tie line, or sometimes we say point of common coupling. So timeline control is really required, because our microgrid, sometimes we are taking input from PV, power supply from PV, battery, and wind. They are really not stable. So we cannot just connect to our traditional grid, because it can disturb the traditional grid. So in this case, suppose if it is like without microgrid control, the assets are there. So you can see there sometime up, down, power supply consumption is there. But just if you will use tie line control, you can see if we are using our microgrid controller. So if you see from where we have highlighted this line, after that you can see it's a very steady line. So the microgrid controller, based on your set point, you can put the set point on the point of common coupling or tie line, and you can say, okay, this is the required power you can import, or this is the required power you can export to grid. And the good thing about, because the power which is being generated by microgrid controller, the power which is being generated from microgrid by using microgrid controller, it is very stable. So before importing, exporting, it will always check voltage and frequency. If it is matching with the traditional grid, then only it will allow. Otherwise, unless it's not matching value, voltage and frequency, it is not going to close the breaker between traditional grid and microgrid. So that is very stable power. So here, when we have the set points, like though. So based on our set point, that much power only can be exchanged. So this is the benefit to having the microgrid controller. We can control the tie line philosophy. Then second use case, I have like demand charge. So basically demand charge and peak saving. The situation, suppose sometime we have some like a small kind of factory or a small type of premises where suppose we need some, usually we are using 2 kilowatt, but for some afternoon, sometime for like half an hour, we have to use like 2.5 or 3 kilowatt power. So of course we have to reserve a 3 kilowatt power from the traditional grid. And we see that this 1 kilowatt we are using only for 1 hour or 2 hours, and we are going to pay for 22 hours extra, we are paying for that. So with microgrid controller, what we can say, we can analyze what is the peak timing and how much is the load we have to consume during peak. That peak load we can control with our microgrid controller, and we can say that this peak energy you have to use from your renewable resources. So in this case, we are going to save at least the 22 hours price, which we are not using actually. And somewhere it's going to help the traditional grid also, because they have to reserve this much load for someone who is not using, they can utilize somewhere else. Then we have one more use cases like e-car integration. So if suppose you don't have microgrid control, in traditional you have microgrid, and there you have options for e-car charging. Suppose one car came and they put the e-car charging. Okay, you have some like suppose 5 kilowatt something. First car came, he is taking. So what maybe it can do, it will start by charging 5 kilowatt to first car. Maybe after 5 minutes, second car came. So I don't know, like we don't know how it will behave actually. So in this case, microgrid controller, what he can do, suppose you can write algorithm. As I said in the beginning, it's a fully like configurable. You can write, you can design whatever you want. So in this case, you can say, okay, first car came, I want to charge with 5 kilowatt. Second car came, okay, let's divide half, 50-50. Okay, third car came, let's divide 1 by 3. Fourth car came, no. Let's first charge first 3, then once like first in, first out, first charge, then let's start fourth one. So it's like totally up to you what you want to do. You can just really manage your all the assets, power, energy, everything. Then the last one, it is, I would say, it's a really good example, because being a very remote area, sometimes suppose you have somebody, I can take some example where they can have like one battery system with battery inverter, and they can have like one PV solar panel, and with one normal PV inverter, they can just lay some power cable line where battery and PV, they can talk to each other, and battery can control that microgrid basically, because most of the battery they are like grid control. They can form the grid because their voltage and frequency it's stable. So suppose somebody has this kind of things, only like few batteries and one battery system, few PV and PV inverter, they have normal like that. In this case, what it can be do, they cannot control anything. Like it's a totally battery inverter only will control what to do. But in this case, if suppose we are using microgrid controller, so in this case, what you can say, like you can just fully say like, suppose in daytime you are getting power from PV control, you can say that whatever PV we are getting, first let us charge the battery. If battery is charged up to this level, okay, now you serve the load. And suppose you have 3-4 loads, what you can say like, okay, you charge the battery is fully charged. Now what you do, you can directly from PV you can serve the load. Suppose PV gone in night time, you can say, okay, now load should be served from the battery because battery already charged. And there you can like define, okay, up to this situation, you charge all the 4 loads. And as soon as you're reaching some 85%, you have to trip one non-critical load based on priority. So he can trip the load 4. And suppose still there is things going on, there is no power from PV, it can again for some certain situation, certain SOC level. It's like SOC means it's a state of charge level of battery. If it is reaching to second level, it will trip second load like that. It's trip, and there is one level of battery which is always required, because battery is the assets who can form the grid. In blackout conditions, you really need at least few powers. So after that level, you can say set all the loads. Now battery will be equipped with that amount of power. So with microgrid controller, you can have like facilities what to do with your assets based on your priority, and it can change anytime. It's up to you. You can have the set point. You can run the last slide where I shown you. You can run in resilience mode. You can run in economical mode. You can run in stability mode. So everything can be decided by microgrid controller. You can decide your assets. You can decide your powers, what to do, how to do everything. These are the like some overview of some benefit what you can achieve by using microgrid controller. I think most of the things what we discussed in earlier, it's very generic. Like it's a nowhere connected that only this kind of device you can connect with microgrid. It's open. Any open standard platform network devices can be integrated. It's not related with any particular dependency regarding OEM or something. It's free, open. It's with the standard. Any device which is having designed with standards, it can be integrated. And we can have like redundant also in microgrid controller. And it's a by default inbuilt cyber secure with the latest 62443 approval standard. And like we have many certified certification from like IEEE, IEEE, and even some German standards also, and it will operate very fast. So the cycle time is very fast. Like it's very you don't have to worry much. It's very fast. Like sometime in millisecond also it will operate. And it's a grid code compliant and future proof, means you can expand whenever you want. It's nothing like that you have to purchase new hardware or something like that. You can utilize the same existing network. You can just expand it. And it can be used in very harsh environment, like I think even 60, 70, 80 degree also. And it is also having the capability to be operated in EMV environment. So just I will briefly go what is the platform which Siemens is using for the microgrid control. So we are using one hardware and software which belongs to our Siemens CCAM platform. So this CCAM platform, actually we are using around more than 85,000 unit worldwide, and this kind of our devices or units, they are being used everywhere. Like if you start from the oil and gas, like heavy industry, generation, transmission, consumption, even distribution also, we have so many devices from CCAM family, even our Protect 5 relays and all these things. So in the same family, we are using our CCAM microgrid controller, and that will help you somewhere like for easy maintenance kind of job, because it's very big family. So this is our microgrid controller. It's very like compact, and you can install on DIN rail. It can be expandable and all these things. And the best part is about that it has been designed by keeping in mind the latest trend. Latest trend now, whenever we will talk about digitalization, one like main first thing it will come in mind, security. So cyber security, it's inbuilt cyber security, and if you can see, It is approved with latest IEEE 62443 maturity level 4. So, and it has like future signature proof firmware, and we have some kind of logging system which is not which is non volatile. Like suppose device if you're restarting, then also log will be there, and it will support like all the latest technology like VLAN support. There is inbuilt firewall also, and if you can have, if you want, you can have hardware firewall also separately. And the best part, like it can be expand any kind of way. You can have like a redundant system, you can configure new functions, so it's fully modular design. And this is just a small network, I want to say. Like downside you can see you have asset level, then you can, the second level you can have like smart devices which can talk to, because some devices, like suppose if you are bringing some the devices which is really very legacy device and they are not supporting any latest technology, latest communication protocol, there you can have some intermediary devices which can talk to them and can get the data and they can transfer to a microgrid controller. So that's second level. You can see I have shown in second level like a grid code. So basically we have our Ciprotec 5 devices which will directly talk to, like always being communication with our traditional grid. From there it will take the input and it will just match with our microgrid. If everything fine, voltage, frequency, grid is stable, then only it will close the breaker with traditional grid and it will start exporting, importing or any kind of communication with traditional grid. And upside you can see we can have our microgrid controller. We have many options. We have inbuilt web browser capability in our microgrid without having any separate HMI. You can configure like many kind of dashboard, information, even control, monitoring, everything inbuilt over web browser. But if you want like big dashboard, you can use separate, this is what I'm talking. You have inbuilt graphics and it's a free actually inbuilt with our microgrid controller. You can configure whatever you want. You can configure the control, you can configure the status, and you can see whatever things is there. So it's a like free. It's a user friendly. You can configure and you can decide what to do. And but if you want like big information, better information, better trend graphics and many other kind of functionality, we have like optional HMI system where many inbuilt templates are there and it's user friendly. You can define any kind of new template as per your requirement, and it supports many features like reporting, monitoring, controlling, archiving, and like it's totally user friendly and can be configured as per your requirement. So this much from my side. Thank you so much. I'll hand over to my colleague Deepak.
Good afternoon, everybody. We spoke about how to use softwares for grid stability and how to make a better planning of grid, and then we talk about coming down a level in down of microgrids, where we talk about smaller grids, self-sustained grids, with obviously support from the traditional grids. But when you come as a end user, like for example NEDC, who are maintaining the assets, where for them, how does digitalization help them? How does it help them to improve their asset health? How to monitor the health of the assets? How to improve efficiency of the assets? How to faster localize the faults, for example, and how to restore the faults faster. So these are the challenges that you face day to day even in the traditional distribution network. So we will see today how IoT can help in solving such challenges that we traditionally see in the distribution network. So let's see what are the common challenges that across the world, different utilities, even not only utilities, even if you take this, industries as well, they face. So one is unplanned shutdowns because failure of the asset. Let's say the regular maintenance of the switchgear was not done in time, or the cable was not plugged properly onto the switchgear. So it created a fault condition, and this fault condition led to arc flash, and then it created a fault on the switchgear, and then you lose your asset there. Then coming on to fault management, you can have faults. For example, if you take an overhead line network in the distribution network, when there is a fault on the overhead line, your primary station trips, but then you don't know exactly where is the fault. Then you send somebody on the line, throughout the line on a vehicle. They travel through the line, they see where exactly the fault is, and then they do the restoration action. Uh, Coming to substation side, primary station, you have protection relays. You do changes on the protection relays. So you need a physical device to do the testing of the protection relays. For example, and let's say if there is a fault in the station, you want to simulate that fault in a lab environment to see what exactly happened. So you need a software which can help you that instead of having a physical relay with you, you can simulate the fault on a virtual relay, which will replicate the actual physical relay. So in that way, you can faster analyze the fault without having to connect, let's say, your relay with Omicron kit, correct injection kit, and then do the simulation. So this is something that we try to solve here. Energy monitoring. Everybody is talking about CO2 emissions. That is a main topic of IEEE PowerTalks this year as well. So then in that case, you need to know how green is your energy, how much is your consumption, where are the places that you can optimize. So for this, you need information. For example, we take the information from the meters, from the protection relays, and these data are then correlated together with an analytical software that will tell you like how much of your energy is green, how much you're taking from the grid, which is, let's say, for example, if you take microgrid, then you have your own generation with solar, with diesel generators. So in that case, solar would be green, diesel generators would not be obviously green. So in that case, how we will know that how much of your overall energy is green? So we have this challenge as well. Then already Manoj mentioned about EV load management. So even I was speaking day before yesterday about the same topic. How, let's say, when you have EV infrastructures coming up more and more, like for example, within Oman, there is a target by Ministry of Transport that by 2040, 34% reduction in CO2 emissions in the transport sector. So that means how do you achieve it? That means you need to have more and more e-vehicles, even for public transports, even for trucks. So you will see this happening in the coming years in Oman as well. The problem is when you have charge, then you need to have a good charging infrastructure. And when you connect chargers to the grid, then the grid has issues that how it can manage, like the plug in and plug out of the cars are not constant. And when it comes to truck, like cars, maybe they charge in 45 minutes, but the trucks don't charge in 45 minutes. They take 6 hours to charge because the batteries are bigger, the capacities are bigger. So then you need to have a load management system so that which can easily distribute this power within the limit set by the distribution operators like NEDC. So if NEDC says this particular station, the maximum capacity is 900 kilowatt. So even if 10 cars comes and plugs, we never cross the limit of the set by the NEDC. So this is something that we need to take care. So we have this challenge as well when we see more and more EV infrastructures being developed. Finally, cybersecurity. So when we talk about interconnected systems, even let's say today when we talk about let's say a OETC station or an NEDC substation, we connect relays and then we connect to an RTU, and RTU is connected to SCADA. So that means we are interconnecting systems, and the SCADA, we have a lot of softwares running in the SCADA. So that means there are that we use even commercially available softwares like Microsoft operating systems. So that means they are vulnerable, right? So every software, every electronic component, they have something called programs written into it, and these programs are written by human beings, right? So we make mistakes. Now the challenge is if this mistake can lead to a situation where if there is some particular security vulnerability, so that a hacker, for example, can get access to those vulnerabilities, he will utilize those vulnerabilities to get access to the system. So then what what generally a responsible OEM does is that we take feedbacks from all over the world. Like we take feedbacks from researchers, we take feedback from ethical hackers, even from customers, even from our own research and team. And then if we find such vulnerabilities in our products, we declare it publicly. We tell that what is the solution for that. Now the challenge for the end user is that he has a huge fleet of assets, right? He has huge number of protection relays, RTUs, softwares. Now how do they know that which of the stations are affected with this vulnerability? So this is a big challenge for any utility. The next is, let us talk about if there is an incident that is happening in a station. For example, somebody is trying to getting into the engineering workstation with wrong password. He's not authorized to do it, but he's trying to enter into the system by entering wrong password. This would not be detected unless somebody is there in the substation. But then somebody is trying to do it, and finally probably he's able to successfully enter into the system, and then he changes the parameters in the protection relay so that it does not trip when there is a fault. Now what the challenge is, this whole incident will go undetected if nobody is there in the substation. So that is where we need to have something called incident management, where all these kind of incidents can be recorded, and then there is a software that will tell you abnormal action is being performed in certain locations. So then you need you need something called incident management. So for all these different use cases, what we come up is that like we have solutions, like not only us, anybody in the market, they have different solutions for different use cases, and they are not unified. So the challenge for any end user is that they have, for example, for vulnerability management, they have one software package which is not seen by somebody. Then for fault management, you have one software package. Then for condition monitoring, you have a different software package. Now there is no universal view of all these different aspects of the same substation, for example. You need to switch between different softwares, different applications, and then it is really confusing for the end user to manage the system. That's where we come up with a platform called Electrification X, which unifies all these different use cases in one single platform. So based on what the customer wants, they can choose what they want. But the good thing is they see all these different use cases in one single window. So that, for example, I can give you an example that, let's say a tree falls on an overhead line. This will cause the primary station to trip. These two incidents are correlated. So if I have a solution that can only monitor the overhead line but not the primary station, then I will not be able to correlate that these two are because of the same reasons. That's where unifying all these use cases into one single platform will help you, that you see both these faults on the same dashboard. And then you can correlate immediately. The software itself will tell you that this line tripped at the same time the substation tripped. That means they are both correlated. So this is the kind of benefit you get with unifying the different use cases into one single platform. So these are the different, at present, these are the different modules that we have within the software. We have like EV load management, we have network fault management, we have asset management, we have OT companion, you have huge distribution RMU networks to monitor. So we have software solutions to monitor the RMU networks. And also finally the energy and sustainability reporting tool also we have within the same application. In addition to that, we have some other software packages. For example, we have a software called Semaris Control, whereas Electrification X platform is a cloud-based platform. In certain cases, the customer is not yet ready for cloud adoption. So in that case, we can still do condition monitoring using Semaris Control. Then Ciprotec Digital Twin, we are already displaying it in our booth this, which is a virtual copy of our Ciprotec 5 platform of protection relays. And then finally the SIM, at present SIM is outside the Electrification X, but we are also working that in future SIM will also be integrated to Electrification X. I cannot, because of the time, I will not be able to go into all the modules, but we will look into some of the critical applications. So let's take physical assets. Maybe some of you must have already seen it in your experience, that when there is a fault on the switchgear, I'm not talking the fault outside the switchgear, but within the switchgear, it damages the switchgear. The problem is, generally people do is they do regular maintenance. They have periodic intervals, like for example, somebody was telling me yesterday that in MEDC it is once in 2 years. They do maintenance of the system. But what happens within these 2 years, right? For example, or it can also happen that somebody plugged a in this particular case, the contractor who was plugging the cable, he did not use the proper bolts. So then this fault does not happen in a day, right? It accumulates. This condition accumulates over a period of time, and after one point of time, it creates a flashover. This is a wind farm in Germany. They were having 3 windmills, which is connected to the grid, and because of the wrong termination in the cable, it caused a flashover. And the problem is not the failure of the asset. The problem is that they are not able to generate revenue, because whatever generation they are producing cannot be connected to the grid. So they are losing revenue in that case. So in this particular case, they were not able to supply to the grid for 6 months, and that led to a revenue loss of 3 to 5 million euros. So this is something. These values will be different for different applications. If I take data center, for example, this would be even much higher for data centers, because they are dealing with a lot of data. So this is a normal, or common causes for failures in switchgear. So it can be loose connections, humid and corrosive environments. It can be incorrect human work that we saw in the last slide. Insulations, failing of the insulation, maybe it can create partial discharge, for example, or faulty equipments that can that is used in the process. So to monitor all these things automatically, instead of relying only on periodic maintenance and expertise of respective engineers, we can do it automatically, that we install certain sensors on the switchgears. We do different modules, like for example, as basic as temperature monitoring, which could have avoided what we saw the previous slide. This could have been avoided by doing temperature monitoring. We can monitor circuit breakers, we can monitor partial discharge, we can monitor humidity. So by combining all these different sensors and the data coming out of these sensors, we provide information to the end user that if everything is okay. We not only provide information that what is the temperature at like now, what is the temperature. We also tell you if it's okay or not okay. Yeah. So this is the kind of analytics that we built in the software, so that even without a periodic maintenance, you can still rely on the software data that is coming out of the application. So this is just a dashboard. So you can map all your assets, all your substations on this on a Google Map kind of view. It's geotagged, and you see different like red color you see on this slide. So that means there is an alarm in that station, and then you can click on the station. You can go deep down. You can see, for example, if it is in the incomer, if it is in the outgoing, or if it is an air insulated switchgear, whether it is on the cable compartment, whether the problem is in the busbar compartment, or if the problem is in the breaker. So all these different analysis we will provide in the softwares, so that you get better view of your physical assets that you use in your system. It's just an architecture. Because of the lack of time, we will not go deep, but generally these are the sensors. And then we connect to a gateway, which will then connect to the cloud application where all this analytics happens. Next is fault management. So fault management, if I go back to the distribution network example, you have overhead lines, you have RMU networks, and then above that you have your primary substations. Now the fault can happen anywhere. Like it can happen in the transformers, it can happen on the lines, it can happen on the underground cables. Somebody is drilling on the cable, municipality is drilling and they drill on the cable, so it's again a fault. So now the challenge is how to make sure, or how to localize the fault, how to locate the fault faster, how to use technology to locate this faster, and then you can that time you saved to locate the faster will help you improve your restoration time, so that you're faster, your customer gets the power back even faster, because you know where exactly the problem is. So let me go here. So if I take a fault in the substation, so in a substation, when there's a fault, for example, if you have a SCADA system, a SCADA system says, okay, this particular bay has tripped. But now the challenge is they do not know exactly what the fault is, what kind of fault is, what fault current the fault happened. So then you need to send a protection engineer to the site. He connects to the relay, then he downloads the fault records and then carries out the fault analysis. What if all this data is available in his phone? Like he has access to this application. He just logs into the application. He gets, for example, even he gets an email notification when the trip happened, and then he logs into the application. He will see all this different information in, like say, if he has a tab, if he has a laptop, he will see all the information, for example, where the fault happened. Let's say fault happened in multiple locations at the same time. So they will see that it's correlated. Let's say if it is, if I take a transmission station, it can be line differential as operated. That means two substations has operated at the same time. So he can immediately correlate. Then he can see the fault records on the app. So he does not have to download any software to a third, for example, SIGRA to visualize the fault records. In the same application, he can visualize the fault records and then he can suggest the corrective actions without even having to visit the site. So this is the benefit of using IoT, that is, you take data from different devices, finally send it to a centralized software which will do all this analysis and all this reporting to you. So this will help you in faster fault restoration. So again, this is the view. So you can see here the visualization of the fault records. On the right side, you can also see what is, for example, what is your ordering code of your relays, what is your serial number of the relays. Even you can also, it is not here, but you can also see the different parameters at the time of the fault, like what was the fault current, if it's a distance protection, at what distance it operated. So all this different information can then be seen in the app. This is again just the architecture. So you have your devices, if you have protection devices, you have your PQ meters. So we take data from all these things and then send it to the software application. Okay, this I think I can skip. Let me go to this one. We were talking about cybersecurity. So this on the left side is the number of security vulnerabilities being reported on software and hardware components throughout the different years. So you can see as and when we come to the new, because more and more softwares are being used, more and more, even protection relays are becoming more and more intelligent. So that means there are many software components even within the protection relays. So the vulnerabilities report has been going on increasing, new vulnerabilities have been reported. And then the other challenge is incident management. So for example, these graphs, what you see here, it says how many days it took for the incident to be detected and how many days it took to restore. So for example, if you take the first one, incident was happening in the system for 204 days and nobody noticed it. And then finally something happened. The problem is after something happened, to restore it back to the normal condition, they take like 73 days. So this, for an OT system, it's not acceptable. Like you need to be always available. You need to be supplying power to the consumers. So for us, there is no option that we need to be faster. So these are the two use cases that we have solutions for. One is OT companion, as I mentioned. We collect the data of all this software and hardware components that we have in the station. We take data like firmware versions, serial numbers, what are the different softwares installed. Let's say if you have an HMI PC engineering version, what are the different softwares installed, which versions of the softwares are installed. And then finally we see in one common page, you see the whole assets, not only in one substation, but all your substations, all these data are available. And finally, we link it to our vulnerability database. So when I talk about vulnerability database, I'm not talking about only Siemens products, but we also monitor third-party products as well. Like it can be our competitors' products. It can be products like Microsoft. So we take this data and then tell you, are you really affected with the vulnerability? Because, for example, Microsoft will say that this software has a problem. But if you're not using that software, then it is not applicable for you. But for that, you need to really know whether you're really using that software, or if you're really using that protection relay, for example. So that is where OT Companion helps you to tell you that where exactly you need to focus, which substation may be affected, which component is affected. This is the software for incident management. So that means when there is an incident, we saw that incidents do not happen in time in a day. For example, if you have heard of Ukraine cyber attack in 2015, it happened in December 23rd. That at the same time, three substations were attacked at the same time. They started opening the tie breakers or the incoming breakers from remotely. There is YouTube video, you can just search for that in the YouTube. You can see an operator as taking the video in the mobile phone. He's not able to control. Somebody is controlling from remote and opening the breaker. The problem is, it didn't happen on December 23rd. This process did not start on December 23rd. It started in 6 months back. That means they sent an email to the employees with the virus. That virus got infected on the IT network. The IT network, it did a scan on the IT network. It found some open ports. Then it found that some of the engineers are using VPN to connect to the substation to do maintenance. And then the password was cracked using keyboard loggers. Like, you can install software which will tell you what keys you're entering. They cracked the password, and using that credentials, they were able to access the substation remotely. And they opened the breaker, they corrupted the firmware of the RTU, they shut down the inverter, and all these things. And for 16 hours, they had to do, because to restore the power back to, because 225,000 people were affected. And to restore power, they had to rely on manual operations. SCADA was not there because the software was corrupted in the substation. The RTUs were corrupted in the substation. So that means it took 6 months. There was something happening in the system for 6 months, and it went undetected. That's where security incident event management helps. Like, we collect the logs that all these software components are generating, and then we put a software brain. It will analyze all these logs, because let's say if I take a Windows machine for an example, it creates thousands of logs in a day. It is not impossible for a human being to read through 1,000 logs. And you imagine you have thousands of these kind of devices on the network. Then you need to have a software that can read it, do the analysis, and tell you what is the problem. So that is what SIM helps you. It combines all this software intelligence. It takes logs from all these different devices. For example, as simple as, let's say, somebody tries to enter to the engineering workstation. He is not allowed, so he does not know the credential, but he tries passwords multiple times. Now, if nobody is there in the substation, you will not realize it. But if you have a software that is looking at all these things, it will say, hey, in this substation, somebody is trying to enter with 5 times he has already entered wrong passwords. That means you need to look at the station. Or let's say a protection engineer, he knows the username password, but he does not have the permit to go to the substation. He visits the substation, he changes the parameters in the relay. How you detect that? Like, the parameters have been changed, right? So the logs generated, because most of the modern relays, protection relays, they have something called inbuilt logs. It will tell you somebody changed the parameter. So if this information is available to a software will tell you that in this station, somebody has changed a parameter. These are the different use cases. These are not only one. As you see, we have 300 or more than 300 use cases, intelligence into the software, so that these different 300 alerts can be generated. And we are continuously growing, because cyber threats are not stopping. It is continuously evolving, and we need this intelligence to be continuously developed. So we have software applications. We continuously put our development team to continuously develop these rules sets. So just in the beginning, we saw the different challenges and how our different software packages map to this use cases. So this is like, we have different software modules, and all these different challenges that we mentioned earlier can be mapped to all these things. And the best thing is, all these things you see in one single platform. So, thank you. Thank you.
Thank you for this presentation. I am Badr from NADC. I want to know about digital twin in Arabic, if possible. Sorry, because معناها hey ODMS.
ODMS الاسم تاع البرودكت اسمه كده. ODMS موديل مانجمنت، يعني رسمة الشبكة أو الماب تبع الشبكة كديجيتال فورمات، يعني صورة طبق الأصل لحالة الشبكة بطريقة رقمية.
جميل.
نعم ODMS هذا سوفت وير يحدث لك شبكة ريل تايم.
ممتاز. أشكرك.
الله يحفظك. شكرا.
You are last. About fault access in substation. I don't know this. يعني can you give me some skills from grade up to customer? How you manage this fault?
As I said, we have different software modules. Like, for example, you start from the primary substation. So we have softwares which will collect the data from the protection relays. These protection relays, when there's a fault, it will obviously operate, and then a fault record is created. So this events, the fault record is sent to the software. Now let's take overhead line network, which will again in the end go to the final consumer. So then in overhead line network, you have a long, like tens and 20s kilometers of lines. Now what do? We put sensors on the line, on the conductor itself, to check if there is a fault. And these sensors are directly connected to the software. These sensors will tell you where exactly because these sensors are geotagged. That means it will tell you the location of the sensor. So then automatically there will be a map saying that from this substation, the line goes like this. Then it has a branch. It goes on the left, on the right, to different places. And then when there is a fault, like let's say a tree falls on the line, this will be a permanent fault. But let's say a bird shorts the two lines. It's a temporary fault, but station will still operate, right? The primary station will still operate. Now you need to know if it's a temporary fault, then you can immediately restore the power, right? You don't have to wait to somebody go through all the whole network and then ensure that okay, it's just a temporary fault. So you want to restore the power to the consumer faster. So now you have, from this sensors, it also tells you whether the fault is temporary or if the fault is permanent. So if it is permanent, yes, you have to send somebody to that particular location where the fault is. But if it is temporary, you can tell the SCADA that yes, it's a temporary fault, you can immediately close the breaker.
Okay, for this it can be in OHL, right?
Yeah, in OHL. Similarly for underground cable network. So if it is underground cable network, we install RTUs in RMU stations,
Okay.
and we will have fault passage indicators even on the cables on the ring side, and protection relays obviously on the transformer side. We take data from all these three devices and then send the data to the software.
And it's working in low load. Some يعني areas it has load. It's very small يعني.
Correct.
Some protection it's not working in low load.
Right. This is
That's
not,
what we
correct.
are faced in some protections devices.
So these fault sensors itself, the overhead line, for example, the fault sensor itself, they also work on low loads. So you need to set your minimum load when you do the configuration, and then it will detect if there is a fault on low loads as well.
Is it available here in somewhere?
We were
installed in somewhere.
We have one installation in Abu Dhabi. Oman, I'm not sure whether we have an installation. Maybe the local sales team can tell you. I am from Abu Dhabi, basically.
That's why. Inshallah.
Yeah.
Thank you, Tawfiq. Ahsant.
Assalamu alaikum. Thank you very much for all your presentations. I have a general comment or a general inquiry. You have shown different type of applications or different type of softwares or modules which are used within the distribution system. but you are not mentioning at all about who is supposed to work with them. You know, one of the difficult aspects we have in nowadays is that we have short of very good engineers, and in particular those who can do the analysis, who can identify the problems, who can, make assumptions, interpret the assumptions. So what is your suggestions in terms of our engineers to be able to deal with these systems? You are giving a general statements which are as if we have very perfect engineers. So we need from your side as well to highlight on those sides.
Thank you so much for the comments. Yes, I think it would be better if we have mentioned who could be the user of each of these products that we have presented today. That's a good point. What we have shown is really let's say, the broad portfolio of products. We are trying to make it simple to the customer by bundling them with the idea of Grid Scale X. In the past, every department, let's say in any DC, used to buy the only software they need only. And then they need to maintain the maintenance and the license separately. Now we are making it simple. We are bundling all the products. You say, okay, you are a utility. You will need all these products, like Microsoft Office. One day you need Microsoft Office across the enterprise.
Yeah, I totally agree with you. But to be able to grasp and take all the data or all the applications or all the information for the utility to utilize the applications, you need someone who can
who can relate to himself that, yes, this is for me. You're right. That's a very, very valid point. Yes, I think next time we should, when we are presenting something, say, look, we are talking about, say, smart metering. This is relevant to the AMI team, and so that the AMI person that is in the room, he will connect with us. Very good.
You need very good power system analyst who can,
exactly.
Can,
because what we said today, I think it covers all the departments. So it covers on different products. So we talk about different product. Each product touches one department or the other. And sometimes 2 or 3 departments use the same product. Example, planning software. You will find it with planning, operation planning, which is in the operation side. So you can find the multiple users for the same product.
The other thing is you have mentioned about the microgrids, you have mentioned about controls of microgrids, and then you have mentioned about the tie point, coupling point. Without giving any figures or any numbers, you should highlight what size of microgrid network for you to be able to use this, or what are the limitations, what are the minimum requirements. It needs more
sizing.
Information there. Yeah, because for us as a sector to be able to utilize it, we need to compare that or to relate that to what is existing, so that one can take a decision on it.
Very good point.
So one thing, like when you talk about microgrid controllers, so it's kind of scalable technology. So that means you can start with a small, like we already did a pilot with Sultan Qaboos University for the students to learn about microgrid. So it's very small environment. I think how many motors?
Very small motors. It's only for lab purpose for students.
Yeah.
I think it's less than 1 kilowatt.
So that's at the smallest level, but then you can scale it up even at a higher. And also, if you see one of the last slide Manoj mentioned here was about scaling, modular approach, where some part of the microgrid will be with one controller, then you have another controller, and then you have a top control. So in that way, you can scale the whole architecture so that even you can include more and more generating. When it comes to IoT, because IoT is a cloud platform, the scalable limit is unlimited, because of the resources available within, let's say, the cloud, because cloud, as and when you go on adding devices or adding data, you can go on purchasing it. It's infinite, theoretically infinite data. So when it comes to IoT applications, it is theoretically unlimited. It's completely scalable. Yeah.
Thank you so much.
Thank you.
Yes, thank
Yeah,
you
thank
for your presentation. I have two questions regarding the smart metering. You told this smart metering, it can be save a lot of data. يعني my questions يعني all this data it can be help us for يعني for different يعني utilities like investigation, history the data. My question about the servers who's يعني storing this data. يعني maybe after 5 years or 3 years they need to come to this data and maybe analyze or some things. And we ask how we can save this. Maybe huge data is require more or huge server to keep this data easily. Yani.
Yep.
This
Yeah.
is my questions. The second questions also about the LV. LV.
Insight.
Yeah. It is good investment for the LV as well as yani, LV. It is will be change depend about the demand. Change yearly or yani, if you investment for this LV side, it is a good investment.
So you like the solution,
Yeah.
having visibility down to the low voltage?
Yes.
Yeah, definitely. We see a big need from multiple utilities to have visibility down to the low voltage, to see the outages, to detect where are the areas where there are more vulnerability, and also to improve customer service, to improve customer satisfaction. If there are outages, you need to quickly detect and restore power. Exactly. That's the very purpose of LV Insight. To your first question regarding AMI data, yes, they are huge. So per day, I'm telling you, in one of the countries, we receive 8 giga every day. And that's a burden. With the time, you need to do what we call a data backup strategy. You say, okay, anything older than 3 years, we go to what we call a backup. So we put it in tapes, right? It's no more into a hot storage, it's in a cold storage. So that's cheaper, but retrieving that data will be a little bit cumbersome because you need to take the tapes, you need to do restore, but there is a solution for that. So there should be a data backup strategy, say 3 years, I need 3 years, I need 2 years, based on your how much you are ready to pay for storage. And now I see some utilities going to cloud. Say, look, it's more efficient for me to store my data in a local cloud than build my own data center. If you have your own storage in your premises, that will cost you a lot. You need always to buy new storage, keep a team that does the administration. But I see today a trend to push the storage to, let's say, a local cloud, Ooredoo, let's say here, or if you have Amazon or Azure or whatever in the country, you store it there, it's cheaper.
I mean, this, it is easy to implement it in our network. I think it will be need investment a lot of monies for this.
Of course, if you do it on-prem, if you do the storage in your data center, it will cost you a lot. But if you take your data storage strategy, you rely on cloud on certain areas, that will be manageable. Or you say, okay, I don't store 3 years of backup, I store 1 year. Okay, it will cost me X. Okay, fine. My studies will not need more than 2 years. Or we can select, say, okay, from this huge data, I will select only kilowatt hour to store. I will not store everything. Because the meter sends around 12 data points. 3 voltage, 3 current, the power factor. So it sends a lot of data. You may decide what I might need in the future to go back and do studies is only kilowatt hour or active power. All the rest, I don't need to store it. Power factor every 30 minutes. Do you really need it? Power factor, you might need it once a day or once a month. So you might go into optimizing what you should store and for how long. And we help customers on those activities. We have a similar problem with the customer in the region. Say, it's cost me a lot, your storage. So now we are into really tuning the optimization of storage.
Yes, yes. Thank you.
Thank you so much. Very good questions, Wallahi. Very pertinent. Yeah. Any question? Yes.
Yeah, good afternoon, everyone. My name is Glenn Picardo. I was working with the utility for a long time with the Federal Electricity Water Authority in UAE. I will answer the question not on a vendor agnostic, but away from it. Yeah, I know it's a Siemens thing, but let me answer it separately. The gentleman was asking the question about interference of engineers into that process. Typically it comes under the ADMS kind of an application, wherein you collect the data, and on top of SCADA, you have this application which does the network study. So that's called the DMS systems. In the ADMS, you have the volt war management. So by and large, you really don't have much of an intervention. You feed in the network parameters, and you get the solution. Fault isolation, there's a typical application called Flizzr. Yes, I think most of the systems today, they address that problem. It's quite a standard feature.
I used to be in OETC, Oman Electricity Transmission Company, for many years.
Okay.
So I know these issues.
Yeah.
It's very important that we address the issue of short of staff,
Exactly.
the issue of expertise.
Right.
It's very important. Sorry. It's very important to address that issue,
Yes.
because the new technology, the transfer of energy, it's very fast. So
Right.
you have to prepare. It's not classically as we used to train our engineers.
True.
You have to train the engineers to be able to cope with the fast transition of energy.
Yes. I think,
Otherwise,
if I'm not mistaken.
the technology is very fast.
Yes.
Every day they are coming with new models, with new softwares, with new applications.
true. I think
If
what-
the engineers cannot cope with that, it's very
What
difficult.
they're addressing is, of course, the future smart grid as well.
Yeah,
When you have micro generations and to manage the stability of the grid.
yeah,
So there it plays a very important role.
yeah, it
You have
is.
the controllable devices. We did talk about it, but I think that's what it is.
Yeah. See, they have mentioned about microgrid.
Yes,
In our system, whether it is transmission or distribution,
yes.
we still don't have microgrids. Now,
Yes, it's a future.
yeah, so to be able to utilize that, you need people to be able to think about it.
Right. I totally agree, yes.
Yeah.
Thank you.
Very good points. Yes, thank you so much. Yes, that's the human resource element is very important in smart grid. Learning, training, and continuous development of the team is crucial. Yeah. Thank you so much. Thank you all. Really pleasure to have you. Barakallahu fikum. Shukran. Ahsantum. Barakallahu fikum.
Sorry guys, just a small note. You can join us on the lunch. The last session will start at 2 o'clock. Thank you.